Hello everyone, hope your day is going well. Remember in previous chapter when we had a multivariable function which you had many variables as an independent and a single variable as a dependent, such as z, which we could really write it as a function of x and a y and write equal to 3x squared y. That's the multivariable function. And you know the graph of this one requires some techniques because the domain of this function is sets of all real numbers in the xy plane. Therefore, for every one of these xy value, you must produce a z value. And pretty much what you're really creating, you're creating a space. Or you can creating a surface into the space. And prior to this lecture, we did study how do we find equation of a line into the space. Remember when we talked about two-dimensional graph, equation of a line was very easy because all you needed is a point like 2 and a 3, and all I need the slope of that line. A slope means the rate of change, and the beauty about the equation of a line is that the rate of change is always constant. Therefore, if I said my slope for every 2 units I go forward, I go up 3 units, and somebody gonna say, well, why you didn't go backward? In mathematics, we never go backward. We always start from negative infinity, go to positive infinity. Therefore, you always have to look from left to right. You're not allowed to look from right to left. And somebody said, okay, what happened about that line? Well, you have to look from left to right. This is a line, you're coming down from the attic. This is a ladder, but this is a ladder you're going up into the attic. An equation of a line was very easy, y equal to mx plus b. B was your y-intercept, x is your and m is the slope, and x and y are arbitrary points on the line. In this case, I didn't give you the y-intercept. I can use the other method, which is y minus y1 equal to m times x minus x1, and this one is nothing except the equation of a slope. I did cross product. Therefore, in your y1 here is 3, your slope is 3/2, and x1 is 2. That's the equation of the line. Then, when you are in R2, the slope must be given in order to write the equation of a line. Somebody said, what happens if a slope is not given? I have to give you another points to use the other points to find the slope using the formula y2 minus y1 over x2 minus x1. Then somebody said, what happens if I'm in a 3-dimension? What is the equation of a line? You have to give me a point, and that point is going to become, must have x, y, and a z. But you have to give me the slope. Well, remember in here, the line can have a different rate of change in xy axis than in xz axis. Or it could have a different rate of change in yz axis respect to xz. Therefore, I cannot give you any specific number because that specific number maybe cover the xy plane in a direction of xy plane, but not the yz. Then somebody say, well, you're not able to provide me with a specific number for a slope. What do I have to do in multivariable? In multivariable, all the slope, which is represented by, which is defines you the direction, is given by a vector. Therefore, I must give you a vector which have same direction as the direction of your line. Therefore, if that vector is 2, 3, and then 1, therefore, I want to write the equation of a line which is parallel to that one. Therefore, if 2 vectors are parallel, they must be constant multiples of each other. Well, you gave me a point, but As a student, I have to have 2 points to create a vector. Well, the second point, one student going to pick this, another student going to pick this, another student going to pick this, another student going to pick this, and I'm going to say the second point is an arbitrary point. Therefore, I can create a vector over that line, which is x minus x naught, y minus y naught, and z minus z naught. And that must be constant multiples of my slope. My slope here is a vector, which is 2 and a 3 and a 1. Sometimes they represent these 2 and a 3, 1 by a real number and call it A, B, C. And these are called directional number. Therefore, equation of a line, x minus x naught must become equal to AT, y minus y naught equal to BT, and z minus z naught must become equal to a CT. These are directional number. This t is a constant multiples. Maybe the length is twice as much, a half of it, a third of it. Therefore, x of the line always can be found by x naught plus AT, y equal to y naught plus BT, and z equal to z naught plus CT. We did talk about the equation of a line into the space, and you must know this one in order to discuss the directional derivative. What I mean by directional derivative? I'm going to give you an example. See, I have x squared plus y squared plus z squared equal to 16. I hope you know this is nothing except equation of a sphere, which if y and z become 0, my x is plus minus 4. If my x and z become 0, y is plus minus 4. Therefore, I have that circle right here. I'm sorry if my circle looks ugly. But if my x and y become 0, my z is plus minus 4. This is easy because I can make that one looks pretty, and that become right here. Therefore, that is the equation of a sphere that really should be look like this. And I want you to assume this is nothing except a gas tank. You cannot store the gas in a cylindrical tank because it is possible for the gas to hide in this corner, and if something happens, it explode. Therefore, in a gas tank is always spherical because you want to provide no hidden corner for that. Okay, I have that gas tank, and I'm going to hire a painter to paint this. The painter is going to sit on the top, and he said, I want to paint it. Does he start painting in this direction? Does he should start painting in that direction? That is painting this direction, paint in that direction, paint at that direction, going back the other one. These are backward, backward, backward. Painter must be able to paint that gas, but it does have infinitely many directions to have his roller going back and forth. Therefore, we studied if you want to paint in the x direction, you can do partial derivative respect to x. That should be parallel to the x. If you want to do it in the y direction, you can do it parallel to the y. This is the partial derivative of a z respect to a y, and that's partial derivative of z respect to x. But somebody said, oh, this is not solved for z. I said, I know, but you have to assume this gas tank, I'm going to put half of it as a semi-sphere on the top and half of it as a semi-sphere on the bottom. And I'm going to only talk about the top semi-sphere, which is 16 minus x squared minus y squared. And I'm going to talk about this one. Pretty much if I talk about this one, then you know about the bottom semi-sphere. Therefore, I know by taking partial derivative of z respect to y and respect to x, I can have the rate of change in these two directions. But what happens if the painter want to come down this way first, all the way, this way, this way? Therefore, I do need to provide you with some formula that you can be able to find how fast the painter is painting the gas tank in a specific direction. Therefore, I'm going to start with a blank page, and I'm going to say, okay, this is your semi-sphere. The painter is here, and the painter is going to come in this direction. Well, this is your y-axis, this is your x-axis, and this one is your z-axis. I bet you in the direction that he is painting is not parallel to the y, is not parallel to the x, is parallel to this vector. And this vector is a vector in the xy plane. Whenever I want to find the rate of change of that painter, how fast he's painting in that direction, I've got to use this vector as my directional numbers. And please remember, you cannot make this vector any vector other than a unit vector, because if the vector is not unit vector, then the magnitude of that one is going to interfere with the magnitude of the directional derivative. Therefore, from today, I'm going to say this vector is a unit vector, call it a u, and that vector is become cosine of theta, which this angle is theta, and sine of theta. Then remember, this is nothing except in a two direction. This is my unit vector, and this is theta, and this become cosine theta, and this is sine theta. What happens if the theta become 0 degree? This is 1 and 0. What happens if the theta is 45 degree? Radical 2 over 2, radical 2 over 2. What happens if theta is 90 degree? Is 0 and 1. What happens if it's a 150 degree? Negative radical 3 over 2 and 1/2. What happens if it's 180 degree? Is negative 1 and 0. Therefore, that theta can be any angle from 0 to 360, and it takes care of every different direction. It's the same thing that you are coming down from a mountain. From here, you have infinitely many different directions to come down. But the minute you get here, you have many directions to come down, and there are some other direction that you can go up. You're always going to have 360 degree rotation wherever you are standing on the surface. Okay, therefore the painter is coming from here to here. Where was that point? It was x naught, y naught, z naught. That was the point. Where did he stop? Maybe he stopped at an arbitrary point. When I project that vector over this vector on the xy plane, the z becomes 0, and that becomes x naught, y naught, and that becomes x comma y. Therefore, that vector must be, which is parallel to that one, must be parallel to my unit vector. Therefore, my x minus x naught, y minus y naught, it is parallel to t cosine theta sine theta. Therefore, I do know that one. My x minus x naught is equal to t cosine theta. My y minus y naught is t sine of theta. And somebody going to ask me, how far the painter paint? Well, it's a distance between these 2 points. Then what is the distance between these 2 points? Is x minus x naught square plus y minus y naught square, which is exactly the same as t squared cosine squared theta plus t squared sine squared of theta. If I factor t squared, you have sine squared plus cosine squared, and sine squared plus cosine squared is 1, square root of t is t. Therefore, I know my distance is a function of x and y is a function of time. Oh, therefore, I know the distance the painter is painting is a function of time. Therefore, I must solve for directional derivative the same way I did derivative of the first single variable as delta x approaches 0. In here, I make my delta t approaches 0. Therefore, I'm going to go back and I'm going to write what we learned in Calculus 1. F of x plus delta x minus f of x over delta x. But in here I have a multivariable. Is f of, that's my x. This is my y. Therefore I have x minus x naught, comma, y minus y naught, minus f of the starting point. And these must be, we said this distance is a function of time. Therefore, it is the delta t. We take the limit as delta t approaches 0. This is called directional derivative, and I have no clue how to solve this, but I'm going to find a way somehow. This is called directional derivative of the function at any given point x and y. Okay, here you do see that from here to here, x change. From here to here, y change. Both of them have changed. In a multivariable function, both of them are not allowed to change. One must stay constant, one must change. Therefore, in here, I'm going to write x minus x naught. I need a comma here. Y minus a y naught. And I'm going to subtract f of x minus a x naught. And I'm going to put right here a y. Okay, tell me what happened here. X stayed the same. X didn't change, but y changed. Some students said, why don't you make the x change and the y become a constant? There is no issue. You can do that too. That's your choice. Make your x to change and the y stay a constant. And students said, where'd you get that from? Out of nowhere. But in mathematics, they said, what you add, you can subtract. Therefore, I added a subtract, and then I put minus f of x naught, y naught over delta t. And I'm going to take the limit as delta t approaches 0. Right now, tell me what it is. This is f of x minus x naught, y minus y naught, minus f of x, comma, y minus y naught over a delta t. But the question is here, what do you see right here? In here, what I see, x minus x naught, if you remember that, it was t cosine theta. This one was t sine theta. This one was t sine theta. Therefore, this is d of t. In here, my x did not change, but my y changed. Therefore, this is the partial derivative of the function. I'm sorry, my x changed, my y did not change. Partial derivative function respect to x. Okay? But the question is here, what is x? I am sorry, x depend on that function, depend on the t, because x and y create a distance. Therefore, what is the derivative of x respect to t? Derivative of x respect to t, remember that's the constant. Derivative of this one is 0. Respect to t, this is a. And your a here was nothing except the cosine theta. And your b was a sine theta. Therefore, what is the derivative of this as a function of t, which is x naught, which is a constant, like 5, 6, 7, plus t cosine theta. Derivative of this one respect to t is a cosine theta. Therefore, in here, I have to multiply by derivative of x respect to t. Then I get my partial derivative of the function respect to t. Okay, therefore, this one is partial derivative of x. What is dx dt? Cosine theta. Oh, what do you see in this part? X did not change. I'm sorry, this should be an x naught. That should be an x naught. That should be an x naught. X did not change, but y changed. Therefore, this is plus This is another derivative. Remember, we can take the limit of the sum is the sum of two limits, and then this would become partial derivative of f respect to y times derivative of the y respect to t. And y respect to t is y naught plus t sine theta, and this is a constant, but the derivative of y respect to t is a sine theta. Therefore, this becomes plus partial derivative of y sine theta. This is called the directional derivative of the function x and y at any given point. But at any given point in a direction of that unit vector. Let me ask you a favor. What happens if the theta becomes 0 degree? What is cosine of 0? 1. What is sine of 0? 0. Then at the theta, directional derivative of the function is nothing except the partial derivative with respect to x. What happens if the theta becomes 90 degree? The cosine is 0, the sine is 1. Directional derivative will become partial derivative with respect to y. That's amazing. Therefore, if you want to find a directional derivative at any other given direction, you have to tell me what is the sine and a cosine. Let me give you an example. I do have a function. That function is x cubed y plus 2y minus 7x. And at the point of 1 and a negative 2, the painter is standing right there. I want to know, in the direction of this vector, which is 3 and a 5, what did that 3 and 5 means? Means 1, 2, 3, 5. In this direction, is the painter painting my spherical tank going up or going down at what rate? Remember, these are called directional number. The 3 is not a cosine theta. The 5 is not a sine theta. They have to become a unit vector. Cosine theta is always x over r. Sine theta is y over r. Therefore, if the vector is not unit, you gotta make it unit. A unit vector. Therefore, what is the magnitude of that one? Is 9 plus 25 is 34. That becomes 3 over the square root of 34. 5 over the square root of 34. Then this is a cosine theta, x over r. This is a sine theta, y over r. Therefore, sometimes when I write the directional derivative of the function at any given point, I said partial derivative of x. I put cosine theta, but sometimes I put adjacent over the hypotenuse plus partial derivative of y opposite over the hypotenuse. This is nothing except a unit circle. Therefore, if I want to take the directional derivative of the painter at the point of 1 and negative 2, let me do it with respect to y first. What is the partial derivative with respect to x? Is 3x squared y minus 7. I have to multiply by cosine theta plus. Remember, directional derivative is not a vector. Directional derivative is a scalar quantity, it's a number. It had to be positive or negative. Plus partial derivative with respect to y, x cubed plus 2. X cubed plus 2 times sine theta. That's cosine and sine. The value cannot be greater than 1 or less than negative 1. It has to be between negative 1 and 1. Right now, I want to know my directional derivative at the point of what? 1 and a negative 2. Well, what is 1 squared? 1. 1 times negative 2, negative 2. Negative 2 times 3 is a negative 6 minus a 7. For cosine theta, you have to put adjacent over hypotenuse or the unit vector, which is 3 over the square root of 34. Plus, when x is 1, 1 cubed is 1, plus 2 is 3. Make sure I don't make any mistake. And the sine is 5 over the square root of 34. And this is nothing except negative 13 is negative 39. I hope I did it right. Negative 13 times 3, negative 39. If I make mistake, please correct it yourself. 5 times 3 is 15 over the square root of 34. And this is nothing except negative 24 over the square root of 34. Tell me, what direction the painter is coming down when I'm here? Is coming down. At what rate? 24 over the square root of 34. I hope you know a square root of 34 is, if it's close to a square root of 36, which is negative 24 over 6, I'm sorry, that's a negative ones. And that become approximately negative 4. Therefore, for every 1 unit he go forward, he come down 4 units. Therefore, that's how fast he's painting the gas tank. This was an example of a directional derivative, and it is extremely important. Therefore, you must know in a multivariable function is different from a single variable. When you have a single variable, you have a path. And you either, and then you want to paint at that path like a highway, you can either go to right or you can go either to left. Therefore, you take the derivative of the function respect to x, your slope is going to be either increasing or is coming down. Therefore, over there, I have only from left and right. I have 2 directions. I don't have to give you any vector because you already know your direction. But when it comes to multivariable, oh, you're standing right here and you must be able to look many different ways. Therefore, in here is a multivariable. You have to have directional derivative. And if I ask you directional derivative, I have to give you which direction. Thank you very much and hope to see you in the next video.